Yes, today we have Maxime Ramzi from Copenhagen, who will be talking about an introduction to dualizable categories.
Yeah, thanks for the invitation. Thanks for the organizers for organizing this. It's such a great seminar to have, and so it's a pleasure to open it this year. So yeah, I'll be talking about dualizable categories, which are kind of a hot topic at the moment, I guess, in some circles at least. And so I was maybe a bit optimistic in the abstract, and I have this pretext theorem that I want to reach, but I don't know if I'll get to reach, and it probably won't get to reach a proof of it, almost definitely. But mostly it's for people to have an idea of why people are excited about this, and sort of what kind of thing we're talking about, what these dualizable categories are. So the plan is as follows. I'll start with a bit of motivation, like again why we care about these things, why these gadgets. And then I'll talk about a bit more about the structure of these gadgets, which will be dualizable categories. And finally, as I said, I probably won't reach this, but if I do, this will be about the presentability of the category of dualizable categories, which is like this pretext theorem that I want to reach. And yeah, don't hesitate along the way to ask questions. I don't think I can see the chat, so if you have questions, please either ask them out loud or ask someone to sort of read them aloud for me, so I can answer.
Or read if there's any in the chat.
Yeah, great. Right, so what is the first sort of motivation that we're looking for? What is the first hint that something might be interesting in dualizable categories? For me, it's THH somehow. So THH is an invariant of many things, an algebraic invariant that originally was defined maybe for rings, and to every ring you assign a spectrum. And it's an interesting invariant for many reasons. You know, for example, if you care about K-theory, it's an interesting invariant to study K-theory, but it's also interesting in its own right. And there have been several like sort of, you know, extensions of its domain. So the first extension of its domain was that you could actually define it for an arbitrary like E1 ring spectrum, which I'll denote for this slide by alg. I don't think I'll ever talk about them again, but sort of you can extend THH to ring spectra, and then you observe that you can actually also extend it further to stable infinity categories. So most of my talk will be based in infinity categories. I won't say too much about this. I hope it's okay with everyone. So, and the way this extension works is that you send a ring A to its category of perfect modules in spectra, and then it turns out that there's a functor here, which is also called THH, for which these diagrams commute. And essentially, the key observation here, the key observation that makes you want to consider dualizable categories is an insight that I probably should have looked up who it's due to. I don't really actually know who it's due to, but is that THH can be viewed as a trace. Can be viewed as a trace in the following sense. So for every gadget here, for every stable category, every small stable category, you can assign its end completion, and its end completion is now a big category, so it's a presentable stable category. And it turns out that it is dualizable for a certain tensor product. So the tensor product in question is the Lurie tensor product, which is some C tensor D thing, which classifies like functors out of it. Co-continuous functors out of it are the same thing as functors out of the product C times D to E that are co-continuous in each variable. So this is the Lurie tensor product. And it turns out, so a key observation is that end of C for a small c is always dualizable, So what does this mean? This is the same dualizable as in the title of my talk. So this is the key word. So maybe I should say what it is. So you have this category of functors from C to D for any C and D in presentable categories, let's say. And one way to create such functors is to take like a linear form, so a functor from C to spectra, which, you know, you should think of this as an analogy with linear algebra. So spectra is like the base field, and these are linear forms, and a scalar, so an object of D. And when you have a linear form and an object of D, you can form a linear map from C to D. And C is called dualizable if for all D, this canonical map is an equivalence. Okay. And what this buys you is that you can always write somehow any linear map, quote unquote, so any co-continuous functor, as a finite sum or like a co-limit of like pure tensors, so linear form tensors, scale vectors. So what this buys you is the following trace function from endofunctors of C. Well, you can decompose those canonically as, again, linear form tensor vectors, and then you can use the evaluation functor here. So if you have a linear form and a vector, you can evaluate this, and you get a spectrum. And this is like a trace. This is a trace map. So if you do all these analogies with vector spaces, this is literally the usual trace of endomorphisms of finite dimensional vector spaces. And yeah, so you can define this whenever C is dualizable. And so, as I said, the key insight is that the int category of a small category is always dualizable. And the theorem here is that THH of the small category is actually the trace of the identity on this big category. Okay, so here I always have the canonical element, this identity. And so this is the key observation here. And so this is telling us, okay, we have this gadget defined for small categories, but I could have defined it whenever I had a big dualizable category instead, right? Here, I didn't need to put in C, I just needed to put something where I can do this trick. And so the conclusion of this is that THH is actually naturally an invariant of big categories, is naturally an invariant of dualizable categories, in fact. Of dualizable, which I'll write DBL categories. Yeah.
There's a question chat. Can you see the additional structure on THH through this point of view?
Yes, it's a bit involved, and I don't want to spend too much time on it, but you definitely can see the additional structure on THH from this point of view. Yes, like so this additional structure is usually like this cyclotomic spectrum structure, and I guess the easiest thing you can say is the easiest thing you can explain is how to see the S1 action. The cyclotomic structure is a bit more involved, and I guess you need more inputs than just this. But for the S1 action, you need just this input. For example, that's a good question.
Does THH of C restrict those for rings?
Yes. So THH for C, when you plug in C equals the perfect category of a ring spectrum, you get THH of the ring spectrum. So that's in the sense that it's really an extension of this smaller one. Yeah. Right. And furthermore, in this conclusion, something that is maybe not apparent from this discussion, but is in fact true, is THH has some extra structure, as was said, but it also has extra properties. For example, it's something called localizing invariant. And it turns out that many of these properties, much of this structure is visible also at the level of dualizable categories. And so, for example, THH is also naturally a localizing invariant of dualizable categories. Also, so I'll write this. I'll say a bit more about what this means later, but I'll write just localizing invariant of dualizable categories. Okay, but you might think this is just a fluke, and like, okay, THH is a trace, therefore it can be defined on dualizable, but maybe this is not so cool. So I'll move on to a second hint, which is now unrelated, but we'll see later that it is related. So this second hint that something is interesting in this direction. Yeah.
The definition of dualizable that you gave, is it also does it in some way imply that if you apply co-continuous functor from C to spectra twice, like if you apply this operation twice on it, will you get back C itself, like finite dimensional vector space?
Yep. Okay. It implies that. Yeah. Yeah. So the analogy is very, very good.
Okay.
So the second hint is that there are some deficiencies in the classical definition of algebraic K-theory. And these deficiencies, as I'll see, they're related to the telescope conjecture or the generalized telescope conjecture. And they're somehow fixed by some theorem called Tama excision. So this is the title of this slide. But we'll see that this fix later, we'll see that this fix is really better fixed by dualizable categories. So where are these deficiencies? So algebraic K-theory, and for me, it will be non-connective algebraic K-theory. Just as for THH, you can define it as an invariant of stable infinity categories, and it's something called the localizing invariant. So what this means is that whenever you have something called the Karoubi sequence of stable infinity categories, which you should think of some kind of fiber-cofiber sequence of stable categories, it's sent to a fiber sequence of spectra. And the cleanest way of defining a Karoubi sequence, you'll see, is a bit disappointing, because the cleanest way of defining this is if, when you take ind completions, you get a localization sequence that is like ind of E is the quotient of ind of D by ind of C. Under the ind completions of these functors is a localization sequence. So like a Bausfield localization. And you can see that, you're defining this by first going to the ind completion and then saying something there. So maybe, first of all, it's indicating that you should maybe look at the ind completions themselves. But now you might be like, okay, how does this tell me that there's a deficiency? Well, now if I have a map from D to E, and I don't have a C yet, and I just have a map from D to E such that the induced map, like this, is a localization. So it's a Bausfield localization, given F such that this is a Bausfield localization. You might want to describe, in K-theoretic terms, the fiber of the K-theory map. So what is the fiber of K-theory of D to K-theory of E? And can you describe it in K-theoretic terms? And you might think that this never really happens. So if you have such a Bausfield localization, then its kernel is always ind of C for some C. But it turns out that this is not always the case. So this is something called This is something called the generalized telescope conjecture, and it's not true. It's not really conjecture. It was a conjecture, I guess, for maybe a year or two or something, but it's not true. So any F from D to E with ind of F being a localization, for any such thing, the kernel of ind of F is itself ind of C for some C. So this generalized telescope conjecture is a generalization of the original telescope conjecture, which involves specific chromatic homotopy theory notions, but you can sort of abstract it away and get this version of the generalized telescope conjecture, and you can ask, is this true? And the answer is, again, as I said, it's no. And in particular, you might be in the situation where this is a localization, and it doesn't seem like you can describe the fiber on K-theory via K-theoretic methods. So there is a fix to this. There is a fix to this, which is that you might just want to define, some virtual kernel or something, which would be like the thing that would be the kernel if there was one, and define its K-theory to be the fiber.
So about that, so by kernel, that's a question. So kernel means fiber?
Yes, kernel and fiber are the same thing. Yeah. I'm saying kernel because in this case, it's really a property to be sent to zero, and it's not really the data of a null homotopy. The point being that the zero object is sort of, it's terminal inside the category, so there's only one way of being zero. That's a good question. Yeah. Right. So what you might want to be tempted to do is, for any such map D to E, you consider the map itself as sort of a virtual kernel or something, and you define the K-theory of this virtual kernel or something to be the fiber of K-theory of things, and then you might hope that this is well behaved. And in a sense, it is well behaved. So there's this theorem of Tammuz, which I think people nowadays call Tammuz excision or something, which tell us that this is a well-behaved notion in the following sense. So if you have a commutative square like this of two such localizations, or two such maps which upon ind completions are localizations, so ind of F and ind of F prime are localizations, and you further assume that this square becomes a pullback square upon ind completion, so ind of this square is a pullback. So, this is ind of the square being a pullback is suggestive of of F and F prime having the same kernel, right? Because if you have two localizations, then the square is a pullback if and only if the kernels are the same. Wait, is that true? Well, it might not be quite true, but it certainly if it's a pullback, then the kernels are the same, and it's kind of suggestive. Well, certainly if this was true, but also, you know, these maps in the F and in the F prime had a compactly generated kernel, then you would expect to see a fiber square in K-theory. Sorry, a Cartesian square in K-theory, because you would have these fiber sequences and the fibers would match, and now you're in a stable situation. So fibers matching actually implies that you're Cartesian, right? So you would expect that this induces a K-theory, that the K-theory square that it induces is pullback, and this is what Tama proves. So in this case, K of the square is a pullback. So this suggests that there's something like this virtual kernel of F, which is sort of well behaved, and that has a well-defined K-theory, and that makes things work. So this is the second hint that something we need to enlarge K-theory in some way. Oops, I put too many slides for this. And this is one of the key motivations to study dualizable categories, is Efimov's continuous K-theory. It's Efimov's extension of K-theory to dualizable categories that deals with this problem. And the reason it deals with the problem, and maybe this is why I had an extra slide for this, is the following observation, which I'll explain a bit more later. The kernels in the big world, so in PRL stable, of ind of F, of ind of Fs that are localizations, are precisely the dualizable categories. Dualizable objects in PRL stable. So this is not supposed to be obvious. I certainly don't think it is, but I'll come back to this a bit later. But this is sort of the key connection between the two motivations that I gave, is that it turns out that these things that want to be kernels of compact generated localizations are exactly the dualizable objects. And so one way to sort of merge like the two motivations would be if you had some way of defining K-theory on dualizable categories that's in a sense matches the definition of THH on dualizable categories.
So about K-theory, there's a question about how it's related to the incompletion of C. Also how it's defined.
So I've taken, so if you take non-connective K-theory, then I guess in a sense non-connective K-theory only depends on the incompletion of C, in the following sense that, I mean, if C is some technical condition could I then put incomplete, which is a very mild condition, then the compact objects of in C are precisely C. And even without this mild technical assumption, it's only a mild completion of C. So you can recover the K-theory of C from this incompletion in a sense. But a priori, there's no clear, I don't know if there's a clearer answer to your question, or maybe the question can be rephrased in a way where there's a clearer answer. But yeah, I guess in a sense, a lot of the key components of the definition of K-theory only depend on incompletions, but yeah. Okay, so the point is that these kernels are precisely dualizable objects, and so if you could define K-theory on dualizable objects, then maybe you could fix this deficiency in K-theory, because you could maybe hope that the fiber of KD to K of E is some kind of extension of K-theory to, well, evaluated on the kernel of ind of F, and this kernel is dualizable. Okay, and so this is exactly what Efimov does. In a sense, he observes that for any dualizable category, so and by dualizable category I specifically mean like dualizable in PRL stable. You can do other things, but this is the thing that I'll mean. He observed that for any such C, there is not only is there I should write this ind of D, ind of E, and ind of F. Not only is there a localization sequence like this, there exists a localization sequence like this with C as the kernel, but there exists a canonical one. There exists a canonical one. And I'll say more about this later, but for now, let's just keep it to that. And therefore, you can define what he calls continuous K-theory, what some people call Efimov K-theory. It's the same word. All right, it's not the same word, but it's the same meaning. So the continuous K-theory of C, he defines it to be the fiber of the map K of D to K of E for this canonical localization sequence. And essentially, because of Tama's excision theorem, this is essentially well defined. But it turns out that you can sort of you can prove that this works well without Tama's excision theorem and actually recover Tama's excision theorem from these sort of dualizable considerations. So I'll write by in quote marks Tama's theorem. This behaves well. So for example, you can prove again that this is a localizing invariant of dualizable categories. It is a localizing invariant. And the sense in which it's a localizing invariant is that whenever you have a localization sequence C to D to E of dualizable categories, so with, I say, inclusion and projection, let's say, so localization sequence. So whenever you have such a thing, and you have to make sense of, you have to sort of specify what maps you allow between dualizable categories, because, for example, if you had ind of D and ind of E, you're only allowing things of the form ind of a small functor between D and E. And so you have to make some similar restriction on the kinds of functors you allow. I'll say a bit more about which functors you allow in a second, but for now, let's just say some restriction on the functors. So if you have a localization sequence with this restriction on the functors, so this is parenthesis, then the continuous K-theories of these is a fiber sequence. So C, continuous K-theory, D, continuous K-theory, E, this is a fiber sequence. Because in this sense, it's a localizing invariant in a similar way that K-theory was a localizing invariant of small categories. Okay, and once you know this, then you can if you had been able to prove these things without Tama's theorem, which in fact you can, then you would be able to recover Tama's theorem from these considerations, because as I said, this square being a pullback, the above square, I have to go back. It's here. This square being a pullback on incompletion tells you in particular that they have the same kernel, and this kernel happens to be dualizable, but they have the same kernel. And in particular, both induce fiber sequences on K-theory, and so really you have a pullback square. So somehow this continuous K-theory is a way of packaging Tama's theorem, essentially. And in fact, this definition that I gave above, I gave it for K-theory, but it would have made sense actually to put an arbitrary localizing invariant here. So F being a localizing invariant. And this defines similarly for you continuous F. So an extension of F to dualizable categories. And it turns out it has the same formal property as continuous K-theory. It's still a localizing invariant. And in fact, what Efimov proves is a much better theorem than what I just said. He actually proves that this construction is canonical in the following sense. You can restrict any kind of functor from dualizable categories to any stable category. So E is stable. You can restrict this along the ind functor to functors from stable categories to E. And of course, there are many different functors, and so usually this has no reason to be any sort of nice restriction map. But if you restrict to localizing invariants on both sides, so localizing invariants, so these invariants that have this property about localization sequences being sent to fiber sequences, then this restriction functor is an equivalence. So continuous K-theory is not only some kind of lift of K-theory to dualizable categories, it's the only one. And similarly, this THH that I had defined earlier using traces, because it restricts to the appropriate THH here, it must be the canonical continuous extension of THH. So THH is, yeah, this is exactly trace. Okay, so this is telling you that this construction that I gave you, it's sure it's a construction, but it's not just a random construction. It's the only thing that I could have done to make these properties remain true. Are there any questions so far? Okay. So this turns out to be a remarkably robust, like, sort of theory of like localizing invariants. So of course, things like K-theory are hard to compute anyways for small categories, so they're not going to become suddenly easy. But it turns out that you can do a remarkable amount of computations that reduce to the computations of small K-theories that are sort of building blocks in the sense of K-theory computations that we just can't do, of course. But you can reduce to these ones. And of course, there are new things that are harder, but many things are not that much harder. So let me give you some examples. I'll come back a bit to it later, but if X is a locally compact Hausdorff, topological space, and I don't mean homotopic type, I really mean topological space here, then you can prove, I'll say a few more words about this, that the category of sheaves of spectra on X, which I'll just write sheaves, is dualizable. And you can actually compute its continuous K-theory. And more general than the K-theory, you can compute more invariants, not every single invariant, but many invariants. You can compute them. You get compactly supported global sections on X with values in the constant sheaf that is K-theory of the sphere spectrum. Okay, so this is K-theory of the sphere spectrum is a complicated object, but you can reduce to that one. If you're into condensed math, there are examples in condensed math that are dualizable, like nuclear ZP modules. Let me not say what this is if you don't know condensed math, but this is some dualizable category, which is in some sense explicit, and for which the continuous K-theory is exactly the limit over n of the K-theory of Z mod Pn. Okay, so again, these are complicated gadgets, but you can reduce these things, and so this is, I mean, all these computations are due to Efimov. At some point, I need to stop saying his name every 2 sentences. And maybe a final one that I want to mention is that there are some naturally occurring sort of, again, in the condensed setting, there are some naturally occurring categories, like, I don't know, I want to say analytic categories related to the complex numbers, for example, whose continuous K-theory is related to KU, topological K-theory. So this is very vague, but it's vague in part because defining these objects precisely will take me a lot more than 1 hour. And also because some of the results are proved and some of the results are conjectural, but none of them are written down. So you know, I'll just stick to this. It's related to KU in some way. Okay, so this is essentially the motivation. Yeah, Vignesh, yeah.
Maybe it's also worth mentioning the above result also is true for THH.
Yeah. So yeah, this result, so this result is true for many more invariants than K-theory. It's true for any localizing invariant that preserves filtered colimits. And you replace K on both sides by whatever sort of invariant you have. And this one can also be generalized a little bit. But again, this is work that's not yet public. So yes. Right. So this is sort of the motivation to understand to studying the category of dualizable categories. and to study, I mean, dualizable categories in general, because, you know, they're interesting gadgets. There are many examples that aren't compactly generated. They're a slight extension of the word of compactly generated categories, as I'll indicate in a second. And they fix some of the deficiencies of K-theory, and they have a relatively, like, yeah, they fix them in a relatively robust way. So to understand this category of dualizable categories and to understand the dualizable categories, one key theorem is the following theorem that's due to Lurie. And it's a really, really nice theorem. It says that
before
if
you
you
move
take...
on to that, sorry.
What,
There's
sorry?
so just before you move on to the characterization. So this nuclear of CP, ZP, is that some kind of general commutation with limits of continuous K theory?
Yeah. So there is a special sort of class of limits that K-theory commutes with. It doesn't commute with all limits, but it commutes with certain classes of limits, and there are limits in the category of dualizable categories, which makes them quite complicated. Which is why you have this nuclear CP module thing that pops up, and not some simpler sort of, I don't know, P-complete Z module or something. But yeah, Efimov proved the general limit commutation theorem. Yeah.
So for that, do you need to input this Kaspersky-Wingis results that K-theory commutes with infinite products of stable categories, or is it independent of that?
Both. So you have to, part of the proof is proving that K-theory commutes with infinite products, but Efimov gives a different proof of that as well, right, based on sheaves. Essentially, in this result of those names that I'm going to mispronounce if I say them out loud, but the ones you said, one key input is that you can sort of loop K-theory, and once you're able to loop K-theory, you're fine, like at a categorical level. And Efimov has this construction that loops K-theory using sheaves, and so you can sort of, yeah.
Thanks.
Okay, so Lurie has this characterization of dualizable categories, which is as follows. So you start with a presentable stable category, and then the following are equivalent. So one is the C is dualizable, is the thing that sort of links back to the first motivation that I gave about THH. The second one, which is not related to any of the motivations, but it's a good it's a practical tool to prove some of the other characterizations, that C is a retract of a compactly generated category, a compactly generated category. So one of the form end of some small thing. Three is that C is the kernel of a compact localization. So C is the kernel, is equivalent to the kernel of L, where L from end of D to end of E is a compact preserving localization. So this is what preserving localization. So this is what makes the connection with the second motivation that I gave with this Tamu excision theorem. 4 is the one that gives you this canonical localization, is that you can take the end completion of C, which means you formally add filtered colimits to C. And if you're worried about set theory, you can make sense of this in many different ways. One is that you can, even with set theory problems, you can actually make sense of this. And one is that you can restrict to some kappa here, some big cardinal here. But because C is co-complete, this has a colimit functor, which takes a formal filtered colimit and evaluates it to an actual colimit in C. This colimit functor always has a right adjoint, which is essentially unit embedding, which is why I call it Y. So it sends an object of C to the constant filtered diagram, like the constant filtered colimit at that object. And this happens to be fully faithful. So this adjunction always exists. And the characterization is that the colimit functor has a further left adjoint rather than a right adjoint. So there exists a Y hat. So this left adjoint is called Y hat in Mark Oiwa's note. I think Efimov calls it YLL because it's a double left adjoint to the lemma, to the embedding, sorry. But I mean, whatever. It's some left adjoint to the colimit functor that sort of spreads out your object. Yeah. But yeah. And so yeah. So the key here is 1 and 2. 1 and 3. So this is the THH motivation, I guess. Motivation. This is the Tama excision motivation, and here this is canonical version of 3. Canonical version of 3. Because once you have this y hat functor, what you can do is you can use y hat to witness C as the kernel of, well, mudding out in C by C. Right? And for general reasons, this localization here will be a compact preserving localization, and you'll have witnessed C as the kernel of well, some canonical compact preserving localization. And here, if you really want to make it a special, to make it a special case of 3, you really need to put some set theory things here in here, but that's not a big problem. Okay. So yeah, this is one of the key ways to understand these dualizable categories is this theorem of Lurie's. I won't go into the proof of that. Maybe I want to tell you the order in which one can prove this. One can prove that I don't know what I want to say. 1 implies 2, 2 implies 4, 4 implies 3, and then 3 implies 2. And what you should have done from the get-go is that 1 is equivalent to 2. And then this gives you a thing. So how does this work? That 2 implies 1 is relatively straightforward once you know that compactly generated categories are themselves dualizables, because dualizables are always closed under retracts. So 2 implies 1 is rather formal. 1 implies 2, on the other hand, this uses that functors out of C. Well, by dualizability, this is equivalent to functors out of C to spectra tensor with your thing. And it follows that functors out of C preserves localizations. And writing C as some non-compact preserving, but some localization of some compactly generated category will buy you that C is a retract of that thing. Using yeah, you have this localization. 2 implies 4. You can prove it using the surprising fact that adjoints as objects in the arrow category are closed under retracts. Right adjoints as objects of the arrow category are closed under retracts. That's sort of something I didn't expect to be true. It seems a bit too naive, but it is true, it turns out. And 4 implies 3 is via this construction here that I outlined here. You do some set theory business to change this big end of C to something more understandable, and then you have this canonical choice. And then I wrote twice 3, so let me erase that one. And then 3 implies 2. What you're going to want to use is that this L, the right adjoint of this L, preserves filtered colimits because L preserves compacts. And therefore also the inclusion of C into ind D will preserve, so the right adjoint of the inclusion will preserve filtered colimits. But because it's a right adjoint of an inclusion, this gives you a retraction of ind D onto C. So this is roughly how it goes. I on purpose went too fast. So don't worry if you didn't get the proof. The result is more important than the proof, I guess, here. Right. This is, I think, maybe if I had wanted to give a proof, but given time constraints, I won't. Okay. So let's try to understand what's going on here. Why this condition 3, that C be the kernel of something of this form, some localization of this form, doesn't imply that C is compactly generated. And so why this generalized telescope conjecture has to fail in general. So the best way I know of understanding this is to try and prove the generalized telescope conjecture and fail and see that in failing we have understood something. So try to prove it. Try to prove it. So let's take a little object X and C, and the way to prove that C is compactly generated is we're trying to find some non-zero map from some compact object in C. And this, for formal reasons, if you can always do this, then this will guarantee that C is compactly generated. So because, here the right adjoint preserves filtered colimits, this one also does. And therefore, you can observe that these compacts are exactly the objects of C. So this is the kernel of my end of F. That are also compact in D. This essentially follows from this right adjoint preserving filtered colimits. So you're trying to find something in D which is compact, which maps non-zerally to X, and which also vanishes upon end F. But here, sorry, I meant end of D here. But end of D is compactly generated, so you can write X inside end of D as a colimit of compacts. And one of those, let's say di0, will have a non-zero map to X. Okay, but now it's only here, and you want to guarantee that it's in here. So how do you do this? Well, you apply, so for simplicity of notation, I'll call this end of F, I'll call this L. So what you can do is you can apply L to this map. Right, and now L of X is 0 by definition because I have an X that's in C. But it's also this colimit of L of di's, right? Because L preserves colimits, but now L preserves compacts, and therefore this map must have been 0 at some finite stage. Let's say di1. This is already null homotopic. Okay, and now you might hope to iterate because you found a di1 such that this map is 0 upon applying L. Of course, it doesn't buy you that L of di1 itself is 0, but the map is 0. So you might think that you're close enough, and you might want to try to iterate. di2, di3, and so on. And you might hope that at some point in your iteration, you'll reach the 0 object, or an object whose L is 0. Unfortunately, there's no guarantee that this process terminates. At no point will you guarantee that L of your object is 0. However, all of these maps, they're all 0 after applying L. So what you find is that you couldn't succeed in finitely many steps, but in countably many steps, this colimit of dik maps to X. This map is non-zero because it factors this one, and this one was non-zero. And now this object, when I apply L to it, I get 0. I get 0 because it's a colimit of things along maps that are 0 upon applying L. So when you apply L to it, it's a colimit of LDI0, 0, LDI1, 0, LDI2, and so on and so forth. And so it's a colimit along 0 maps, so it's just a 0 object. Now you've taken a countable colimit, so surely you're not compact anymore. I mean, you have no particular reason to expect to be compact anymore, but you're certainly omega-1 compact. And so what you learn, in fact, is that while C is not necessarily compactly generated, it is something called omega-1 compactly generated, which is like the next best finite finiteness condition you can impose on a category. And this actually is crucial in understanding the structure of the category of dualizable categories. Not necessarily understanding sort of precisely that it was omega-1, but this fact that there is this bound that you cannot have things that have no omega-1 compacts or no omega-2 compacts, or something that you have a cardinal bound on the generation of your categories is very crucial in understanding the structure of the dualizable categories. And in fact, this is sort of what comes in. So yeah, this is what comes into the proof of this theorem that I wanted to, that was supposed to be my pretext theorem, which is that the category of dualizable categories is presentable. And unfortunately, given time, I won't say more about this theorem, but somehow the key insight here is this observation that every object is omega-1 presentable, omega-1 compactly generated, and therefore, at the very least, you have some kind of inclusion. It's not even a full inclusion, but you have some kind of inclusion into these guys, and this is presentable itself. So that's not quite good enough, but it's the key insight. What I wanted to tell you about instead of this theorem is to keep analyzing the situation of this, this compact preserving localization that we had. Because these morphisms, the problem of these morphism or of this, this omega-1 compact that we found is that even though the omega-1 compact itself, sorry, it's not equivalent, it maps to my C, or did I call it X? I call it X, I think. Although it maps to my X, and it is itself in C, its constituents are not, or they have no particular reason to be. But it turns out you can rewrite this colimit in a way where the constituents are in fact in C, and this is sort of the next crucial insight in understanding the structure of these dualizable categories. So the observation here is that whenever you have a map D to D prime in D, let's call it alpha, such that L of alpha is null homotopic, for general reasons, you can actually you can actually factor it through some object of C. There exists an object of C, which is the kernel of L, such that this happens. This very much uses that L is a localization, but it is true when L is a localization. C, of course, has no bound whatsoever. So even if my objects were compact, my C has no guarantee of being compact. But I can still do this. And in particular, I can rewrite my sequence like this, DI1 to DI2 to DI3 and so on. I can rewrite this at every step factoring through a compact not a compact object, an object of C. And now by some relatively standard cofinality arguments, you can rewrite that the colimit of the CIs is equivalent to the colimit of this DIs, DIKs. And so now my non-zero map to X to X, sort of it lives completely in C. And you might think, okay, I've rewritten my colimit of compacts as a colimit of random objects, so it's kind of useless because if they're just random objects, I could have picked X to begin with. Why did I pick these specific objects? And the point is that while the objects are kind of random, the maps aren't. Because if you see the maps, they don't factor in C through a compact object, but in D they do. And so they have some sort of finite range property. So CI to CI plus 1 has some form of finite range. So far, this is not a precise statement. It's really just an intuition. But the idea is that it should behave like, even in C, it should behave like some map that factors through a compact. Of course, in C, it doesn't, but it should behave like this. And this leads to the definition of a compact map, which is sort of the key replacement that you have to do when you move from compactly generated categories to dualizable categories. You have to replace compact objects by these compact maps. So a compact map is a map X to Y such that for any map from Y to a colimit, to a filtered colimit of objects, so this is filtered, there is actually a factorization at a finite stage, but only after restricting to X. So this is sort of recording the intuition that, okay, the objects themselves might be quite large, but the map has some form of finite range. And it's not hard to see that these maps, these CI to CI plus 1 that I had in my previous slide, while the CIs are random, these maps are compact. And I thought I would have more time, but I'll end with So yeah, this was where I was supposed to say that. But I'll end with the following characterizations of dualizable categories, which is the replacement of which tells you how, in what sense they're analogous to compactly generated categories more than just being retracts of them. So it's a theorem that in this form I learned from Dustin Clausen, but some other version of it is actually older than this. But okay, I'll just state this version, and yeah. So I start from a category which is presentable and stable. And the point is we're going to characterize when it's dualizable in terms of compact maps. So C is dualizable if and only if the slogan is it has enough compact maps. Oops. Okay, compact maps. And the precise version is if and only if there exists a set of compact maps. So set. And by set, I mean something small, or I don't necessarily need a small thing, but I need some kind of smallness condition. So I'll just say set for now. With the following two properties. The first property is like a zero detection property, which is very analogous to the like compact generation property, the usual things. So for any non-zero z, I can probe z by some compact map. So there exists some compact map in S and a diagram like this, such that this is non-zero. Okay, so you ask more than just the map from Y to Z to be non-zero. You ask also that it be non-zero on this finite image that you had, this finite range that you had. So this is very analogous to the compact generation situation. And there's a second condition, which is very much non-analogous, and it's very subtle and very crucial, and it's a very interesting condition, is that any map in S can be written as a composite of two maps in S. Is a composite of two maps in S. And so this means that you can split all of these maps in S into many, many sort of smaller bits of S things. And this is very important somehow. All right, I know I'm already over time because I think this is 50 minutes, but if you'll indulge like one more minute, I'll say one more thing about this theorem, is that it allows to sort of understand dualizable categories from an internal perspective rather than the external perspective that I originally gave as their definition or their characterization via Lurie's theorem. And this is very practical. For example, it gives a very hands-on proof, very concrete proof of the fact that the category of sheaves on the locally compact Hausdorff space is dualizable. There are many proofs that don't use this. For example, you can use duality, so covariant duality, or essentially like the proper base change theorem, I guess, to prove this. But you can also prove this by hand with this theorem by observing the following thing. You have a very concrete topological incarnation of these compact maps, which is the following kind of maps. So whenever you have opens U and V of X, you have this good containment relation, which is the condition that you can fit a compact between U and V. So this is a compact. Now this is a compact, in the topological sense. So just a compact subset of X. And the observation is that when this happens, then the constant sheaf at the sphere extended by 0 from the open set U, mapping to the constant sheaf at S extended by 0 from the open V, this map is a compact map in sheaves. And it turns out that this set of compact maps is not super hard. It's a bit subtle, but it's not super hard to prove that it satisfies condition 1. This set satisfies condition 1. And condition 2 is then the analog of the following topological property. Whenever you have a good containment, you can fit a smaller open inside, which is well contained in V and contains well U. And this is sort of a very standard sort of point set topology exercise where what you're going to do is around every point in the compact K, you're going to fit a small, like relatively compact open. And because K was compact, there's only finitely many of those, and so you can sort of arrange them in a nice way, and you have this double containment thing. And so this implies that 2 is also satisfied. And this gives you like a very concrete proof, a very concrete understanding of this, of why this category of sheaves is actually dualizable, rather than some complicated theorem like Verge duality, which of course also tells you a lot, but sort of is maybe less concrete. All right, I'm already over time, so I'll stop here, and thank you for your attention.
Thank you very much. Is there any questions that wasn't asked doing? Okay, so a question is, what is known for continuous K-theory about the standard terms that allow these computation and comparisons of K-theory?
Sorry, can you say that again?
It's a general question about what's the standard theorems about continuous K-theory that allows for computations and comparisons.
So comparison with ordinary K-theory of stable categories is that the continuous K-theory of end of C is just the K-theory of C, whenever C is a small stable categories. So this is the comparison with the classical one. And the standard kind of techniques that go into computing continuous K-theory of a like a genuinely dualizable category is going to be, instead of using like this canonical resolution, so this one, end of D with y hat and the quotient by y hat, instead of using that one, you're going to use some resolution that is more like, you know, relevant for D. So for example, in this nuclear ZP case, you're going to find some resolution that really sort of compares it to maybe something that has the same K-theory as the product of modules over Z mod Pn. So maybe it's not Z mod Pn itself, but something that looks like this. And you're going to find some other category where you have some map here that sort of induces on K-theory the map that you would expect to see if you want to compute the limit. And you can, you can sort of do these sorts of tricks, yeah, and to hope to compute the K-theory of D. So typically what you do is you find some better resolution that is more appropriate to D than the standard one. So yeah.
Are there other questions?
So these products here, these products here are now products of dualizable categories, right?
Yes. Yeah. I also, I'm not, we need to remember, but I also think this is not exactly what you do. You take something that has the same K-theory as this would have, but it's not this category. Yeah, I think it's more like, I think you're supposed to think of like a lax limit kind of thing, where instead of taking the limit, you take at every stage some object, and at every stage some map between this base change and the one at the level below, without asking that this map be an equivalence. I think that's what you're supposed to think of.
Okay, I will stop the recording in case there's anyone who has questions they don't want recorded.